Thank you for joining us for the first part of a two-part video specifically on analysis of variance. This video will build on much of the content that we covered in our previous videos in this series. Therefore, to get the most benefit from this lesson, we recommend that you review that content first if necessary. This video covers the theory behind analysis of variance. While we endeavor to present the content as clearly as possible, this will be our longest and most in-depth lesson due to the complexity of the topic. As always, our goal is to support and clarify your classroom learning on ANOVA. So we will focus on those areas that students often need additional instruction on in order to become truly grounded in the content. We have broken this video down into 6 shorter sections. They are 1. Introduction to ANOVA theory and the null hypothesis. 2. Sources of variation in the data and partitioning the sum of squares. 3. ANOVA calculations. 4. Mean squares and degrees of freedom. 5. The connection between the standard error of the mean and ANOVA. 6. Summary and introduction to our next video. In part 2, we will continue our discussion of making inferences using ANOVA. In that video, we will cover the F distribution, the F test, and the statistical assumptions that underlie analysis of variance. One of the differences between this video and our prior videos in this series is that we will not be including our usual statistical simulations as part of the content. Instead, we have produced a separate video that utilizes a large-scale analysis of variance simulator that will enable us to more fully demonstrate all the topics that we have covered in our prior videos. So, let's get started with part 1 of our lesson on analysis of variance. Analysis of variance primarily seeks to determine if the means of 2 or more groups, sampled from a population, actually differ at the population level. While t-tests are commonly used to evaluate mean differences between 2 groups, ANOVA is typically employed when comparing the means of 3 or more groups. The central question posed by ANOVA is whether we can confidently state that the differences we observe in sample means truly reflect actual differences at the population level caused by our experimental treatment, and are not simply differences that resulted from sampling error. Before we explain how we answer this question, we first need to discuss what the hypothesis being tested by ANOVA is. In an ANOVA, the null hypothesis states that the population means of all the groups, denoted as mu1, mu2, mu3, and so on, are all equal. That is, we are testing the hypothesis that there are no differences among the group means in the population versus the alternative hypothesis that at least one of the means being tested differs from the others. There is another equivalent way to state this hypothesis using the terminology of the factor model of individual scores that we covered in a previous video on that topic. This alternative formulation of the null hypothesis is stated in terms of treatment effects instead of group means. As a reminder, the definition of a treatment effect for a group is the difference between the group mean and the grand mean. The null hypothesis stated in terms of treatment effects is that all treatment effects are equal to each other and are equal to 0. If we had 3 groups in our study, this null hypothesis would be stated as alpha sub 1 equals alpha sub 2 equals alpha sub 3 equals 0. While this difference in expressing the null hypothesis in terms of treatment effects instead of group means doesn't impact how we perform a one-way ANOVA, it becomes essential when modeling the scores in more complex ANOVA designs. When we conduct an ANOVA, we are interested in making a statement about how likely it is that any differences we see in the sample means are actually present in the population from which we drew the samples, or whether the differences are just a result of sampling error that occurred when we selected them. So one of the questions that often is asked is, what is the nature of the population to which we want to generalize our results? Clearly, we did not perform our experimental treatment on the entire population, so a treated population really doesn't exist. In statistics, we would refer to this population as a hypothetical population. It is the population that would exist if we had been able to treat everyone in it. Random sampling from the population and random assignment to treatments enables us to make valid inferences regarding what this hypothetical population would look like if we actually were able to perform our experimental treatment on all its members. As we stated earlier, the question ANOVA seeks to answer is whether the observed variations in the sample means are due solely to sampling error or if those variations also reflect an experimental treatment effect. To answer this question, there are three concepts related to the variation in the scores that are important to understand. The first concept is called the total sum of squares. This is a measure of the total variation in the data. The question that ANOVA seeks to answer is what is causing this variation. Is this variation simply a result of the expected error variance that occurs because individuals respond differently anytime they are measured on anything? Or is it also caused by the experimental treatment in a study? Another way of asking the same question is whether the same amount of variation in the data would have been observed if we simply performed the same measurement on the same individuals, but without subjecting them to any experimental treatment at all. If that were the case, the variation would be solely attributable to random error in each person's score caused by the processes we discussed in our video on experimental error, inter-individual differences, intra-individual differences, and lack of experimental standardization. As you will see, the total variation in the data reflected by the total sum of squares is actually comprised of two other independent sources of variation. These are the other two important concepts, the within-group sum of squares and the between-group sum of squares. The within-group sum of squares is a pure measure of the amount of variation due to random error in individual scores within each treatment group. Because everyone in a treatment group has been treated in exactly the same way, the only cause of variation in the scores is random error. As you know from our study of the factor model of individual scores, any treatment effect that might be present within a group is considered to be a constant and the same for each person within a group. Therefore, even if a particular treatment to which the group members were subjected affected their scores, the variance of those scores would not change. This is because adding a constant to each score in a distribution will have no effect on the variance of the distribution. This is why the within-group sum of squares is purely a measure of random error, unaffected by treatment effects. The other source of variation in the data is termed the between-group sum of squares. The between-group sum of squares measures how much the means of each group, not the scores, vary from each other. This is the way we start our evaluation of whether the group means actually differ from each other in the population. If the group means were equal to each other, then the variance of those means would be 0. We demonstrated this concept in our video on the central limit theorem when we discussed the standard error of the mean. So an indication that the means of the groups are actually different from each other in the population is the amount of variance we measure among them. The reason why the between-group sum of squares is only an indication of whether the means are different in the population and is not definitive is that we are calculating the between-group sum of squares on samples taken from a population. Therefore, there will be sampling error present in the values of the means we calculate from those samples. If we took another sample, the differences between the sample means would most likely be different. Therefore, any differences among the sample means will be due both to treatment effect and sampling error. Taken together, the between-group sum of squares and the within-group sum of squares fully account for the total amount of variation in the data. This is termed partitioning the sum of squares and is expressed by the equation total sum of squares equals within-group sum of squares plus between-group sum of squares. We will now show you step by step how each of the three sums of squares is calculated. For each example, we will show the formal formula for the calculation on the screen, but our explanation will focus on the actual steps you would need to do to perform the calculations. However, we will also highlight the place within the formula that corresponds to the calculations we are making. Of course, we will most often use statistical software to make these calculations for us. But it is important to have an understanding of the math behind the computations if you want to really understand what each of the quantities calculated really means, and how they relate to the conclusions we ultimately will draw when we conduct an analysis of variance. First, we'll cover the total sum of squares. As we said, this value represents the overall amount of variation in the data. It is calculated in the same manner that the sum of squared deviations from the mean is calculated anytime we compute a variance. First, we calculate the mean of all the scores in our dataset. This is called the grand mean. Then we subtract the grand mean from each individual score to create deviation scores. We then square each of the deviation scores. Finally, we add all the squared deviation scores together. The result is the total sum of squares. As we said, it represents the total variation of all the data in our study. The only difference in this calculation and the calculation of any other variance is that we haven't divided the sum of squares by its associated degrees of freedom to form a variance. This is because our current focus is on the total sum of squares as the indicator of the variation in the data. Next, we will calculate the within-group sum of squares. The within-group sum of squares is a measure of the variation that is present within each one of the groups when summed across all the groups in the study. As mentioned earlier, this variation measures the random error within each group and is not affected by the presence of treatment effects. Statistically, it represents the average amount that the scores within each group deviate from their group mean. Here is how it is calculated. First, we calculate the group mean for each of the groups in the study. We then subtract the group mean from each individual score in that group to create a deviation score. Next, we square each deviation score. Then we sum all the squared deviation scores. The result is the sum of squares within each individual group. To complete the calculation, we add the sum of squares for all the groups together. The total is the within group's sum of squares. By combining the sum of squares calculated within each group across all the groups in the study, the within group's sum of squares becomes a more precise estimate of error than any of the individual groups alone would be. Finally, we will calculate the between groups sum of squares. The between groups sum of squares represents the degree to which the group means vary from one another. This is a measure of the treatment effects present in our study. As we said earlier, if the group means were all the same in the population, their variance would be 0, which would indicate that there were no treatment effects. On the other hand, if there are any differences among the group means, then the variance of those means would be greater than 0, which would indicate the presence of treatment effects. However, in a study, we are evaluating the group means of random samples drawn from a population, so differences among the sample means can arise from sampling fluctuation in addition to treatment effects. Therefore, we can't be certain that any observed variation in the sample means represents the effect of our experimental treatment without additional analysis. We will discuss this in detail later in the video. Here is how we calculate the between groups sum of squares. First, we calculate the mean of all the scores, which is the grand mean. Then we subtract the grand mean from each group mean, which creates a deviation score. We then square each of the deviation scores. Next, we multiply each of the squared deviation scores by the size of the sample on which the mean was calculated to account for the fact the mean was based on multiple observations. Finally, we sum all the values that resulted from the multiplication of the squared deviation scores by the sample size. This gives us the between groups sum of squares. As we pointed out earlier, if there are treatment effects present in the study, the between groups sum of squares will be composed of variation due to both treatment effects and error. If there are no treatment effects, it will only be composed of error. While we have been focusing on the sums of squares as the primary indicator of the amount of variation that exists in our data, if you divide the sums of squares by their associated degrees of freedom, you create a value called the mean square. Mean squares are analogous to variances as they represent the average amount of variation that is present in the data. The mean square within groups reflects the average variation within each group and indicates the variability that is not explained by any treatment effects that might be present in the data. It is a pure measure of the error variance. The mean square between groups is the average amount by which the group means vary from the overall or grand mean of the data. As we have previously said, it quantifies the amount of variation in the data that is caused by treatment effects, if they are present, plus variation among the group means that is attributable to error. Here are the degrees of freedom for each of those sources of variation. The between group degrees of freedom are equal to the number of groups minus 1. So, if there are 3 groups in the study, usually symbolized by k, the between groups degrees of freedom would be equal to k minus 1, which equals 2. The within groups degrees of freedom are equal to the total number of observations, n minus the number of groups, k. So if a study had 3 groups with 30 observations in each group for a total of 90 observations, the degrees of freedom within groups would be 90 minus 3, which equals 87. Finally, the total degrees of freedom in the study equals the total number of observations minus 1. So if a study had 90 observations, the total degrees of freedom would be 89. Like the sums of squares which are partitioned into between groups and within groups, the degrees of freedom are also partitioned similarly. The total degrees of freedom will always be equal to the between group degrees of freedom plus the within group degrees of freedom. So to summarize, the within group's mean square is equal to the within group sum of squares divided by the within group's degrees of freedom. Likewise, the between group's mean square is equal to the between group's sum of squares divided by the between group's degrees of freedom. When the null hypothesis that there are no differences among the means is true, both the between group's mean square and the within group's mean square are independent, unbiased estimates of the population variance from which the samples were drawn. This is because both estimates are based on the variances of random samples drawn from a larger population. In our video on random sampling, you learned that the expected value of the variance of random samples taken from a larger population is equal to the population parameter, in this case, the variance. As you will learn later in this video, it is this fact that will make it possible for us to draw conclusions about whether the observed differences among the means were more likely to be due to our experimental treatments or to random sampling error. You may be wondering how the mean square between groups can be an estimate of the population variance, as it is not obvious from the formula used to calculate it. However, in our video on the central limit theorem, we demonstrated how the calculation of the standard error of the mean is connected to ANOVA. We demonstrated that the formula for the standard error of the mean can be algebraically rearranged to show that the variance of sample means when weighted by the sample size is an unbiased estimate of the population variance. The mean square between groups is also calculating the variance of the sample means weighted by the sample size. It's just that the formula looks different from the rearranged formula for the standard error of the mean, but you would get the same results using either one. Therefore, we are including the portion of our central limit theorem video that demonstrates the connection between the standard error of the mean and ANOVA as a refresher of this important point. We will be presenting that video next in this lesson. We are now going to show you how the standard error of the mean is mathematically related to the variance of the population itself. It turns out that the formula for the standard error of the mean can be algebraically rearranged to provide this unbiased estimate of the population variance. First, let's review the formula for the standard error of the mean. It's simply the standard deviation of our sample, S, divided by the square root of the sample size, n. The standard error of the mean is an estimate of the standard deviation of the sample means. But in analysis of variance, we are interested in the variance of the sample means. Because the variance is simply the square of the standard deviation, if we square all the terms in the formula, the result will be the variance of the sample means, s squared sub x bar. Now we can multiply both sides of the equation by our sample size, n. The result of this operation shows that the sample variance, s squared, is equal to the sample size, n, times the variance of the sample means, s squared sub x bar. Now let's take this a step further. You learned in our video on random sampling that the sample variance of a random sample is an unbiased estimate of the variance of the population from which the sample was drawn. Therefore, we can substitute the population variance, sigma squared, for our sample variance, s squared, in the equation. This gives us a new equation. N times s squared sub x bar is equal to sigma squared. This tells us that the variance of the sample means, multiplied by the sample size, provides an unbiased estimate of the population variance, sigma squared. This process demonstrates how we can use the variance of the means of samples to arrive at an unbiased estimate of the population variance. Because the mean square between groups is also a measure of the variance of the sample means, it too will be an unbiased estimate of the population variance, but only when the null hypothesis that there are no differences between the group means in the population is true. In this case, it is an estimate of the same quantity being estimated by the mean square within groups, which is the error variance in the population. However, when the null hypothesis is not true, and there are differences among the means, then the mean square between groups becomes a combined measure of both error variance and treatment effect. In this case, it is measuring something different than the mean square within groups is measuring. A little later in this video, we will discuss how we can utilize this difference between the mean square within groups and the mean square between groups to draw conclusions about whether any observed differences in the sample means were caused by either experimental treatment or random error. Before we move on, let's first summarize what we have covered so far in this lesson. You have learned that when we examine the data in a study, we expect the scores of the individuals on the outcome measure to vary. The total sum of squares is the measure which quantifies the total amount of the variation present in the data. We can partition the total sum of squares into two independent parts, the within-group sum of squares and the between-groups sum of squares. The within-group sum of squares is a measure of how much variation there is within each of the groups in our study. It is based on how much the scores within each group vary from their group mean, and when combined across all the groups is an estimate of variation due to random error in the population. It will not be affected by any experimental treatment that may be present. The between groups sum of squares is a measure of how much the means of the groups vary from the grand mean of all the scores. It is an estimate of both the variation caused by treatment effect due to our experimental manipulations and the variation due to error. When we divide the within groups sum of squares and the between groups sum of squares by their associated degrees of freedom, we create two variances called mean squares. These are the within groups mean square and the between groups mean square. When the null hypothesis is true, and there are no differences between the group means and the population, both of these mean squares are separate and independent estimates of the population variance. Therefore, over a large number of repetitions of the ANOVA, if we were to divide the between groups mean square by the within groups mean square, the result would be equal to 1. Of course, we typically will not be able to run a large number of repetitions of the same study, so in any single ANOVA, we would expect the ratio of between groups mean square to within groups mean square to be different from 1, simply due to normal sampling fluctuation, even if the null hypothesis were true. When the null hypothesis is false and there really are differences in the group means, the two mean squares are now measures of different things. The within groups mean square is still an estimate of the population variance, but the between groups mean square is now an estimate of two different quantities. It is an estimate of the variation in the data that is caused by the differences among the group means, plus the variation that is caused by the random error in the scores. As a result, the ratio of the between groups mean square to the within groups mean square will be larger than 1 in the population. But as we said, when we take random samples from a population and conduct an ANOVA on the data, a ratio of the mean squares greater than 1 might have been caused because there were true treatment effects present due to our experimental manipulations, or simply because of sampling fluctuation. In statistical terms, the question is how large the ratio of the between groups mean square to the within groups mean square needs to be for us to reject the null hypothesis that there are no differences among the group means in the population. That topic will be the subject of part 2 in our video on ANOVA theory, where we will cover the F distribution and how it is used to draw conclusions about the results of an analysis of variance. You will learn how we can use the F test, which is based on the characteristics of the F distribution, to evaluate whether the between groups mean square and the within groups mean square can be considered to be statistically equal or different from each other. You will also learn how we use that information to determine whether we should reject or fail to reject the null hypothesis that the group means in our study are equal to each other. Finally, we will also cover the statistical assumptions for analysis of variance that have to be met in order for the conclusions we draw to be valid. We hope you found this presentation on the basic concepts of analysis of variance to be valuable. We look forward to presenting part 2 of this video to you. Thank you for watching.